In modern optoelectronics, the physical mechanism used to manipulate light establishes the ceiling for your system's stability, speed, and cost. Engineering demands often pull in opposite directions. It is physically impossible to combine maximum optical power handling, zero-signal crosstalk, and nanosecond reconfiguration speeds in a single, cost-effective device. This chart maps those physical trade-offs. We have data bandwidth requirements on the y-axis and the optical power or damage threshold on the x-axis. Industrial and scientific lasers sit in the high-power, low-bandwidth quadrant, where raw beam control matters more than data transmission speed. Free space telecom sits at the opposite end, requiring extreme bandwidth with moderate power thresholds. Data center routing occupies the final quadrant, where massive bandwidth scalability is required at relatively low power levels. We solve these challenges by mapping three distinct technologies, Acousto-Optic, Electro-Optic, and hybrid switches, directly to the scenarios they were engineered for, prioritizing speed on a spec sheet while ignoring physical constraints, like beam aperture or baseline noise, leads to severe signal distortion and high hardware costs. Acousto-Optic, or AO, devices are the standard choice for systems prioritizing raw laser power control over data speed. Moving down the high-power branch of our decision tree leads to Acousto-Optic technology. These devices rely on Bragg diffraction. Ultrasonic waves sent through a transparent medium create a moving phase grating, bending incident light at precise angles. Wavelength matching is mandatory. You must use tellurium dioxide or quartz for visible light, while infrared bands require gallium phosphide or germanium. Because of these material properties, you cannot easily swap wavelengths. Operating outside the adapted range causes a sharp drop in diffraction efficiency and potential crystal damage. You must also size the physical aperture correctly. The effective aperture of the device needs to be 1.2 times the diameter of your incident beam. An oversized aperture wastes acoustic power. An undersized one causes incomplete edge diffraction and disrupts the beam quality. Acousto-optics provide long-term stability for industrial applications, but they require rigid beam sizing and wavelength planning during the initial design. In free space telecom, the primary bottleneck shifts to gigahertz modulation speeds. The high-speed branch of the decision tree isolates pure electro-optic, or EO, lithium niobate crystals. The EO mechanism involves applying an electric field to a crystal to alter its refractive index. This achieves ultra-fast phase and amplitude modulation. The trade-off is the driving voltage. Inducing the necessary phase change requires hundreds of volts, which adds high-voltage amplifiers to your system's footprint. You also have to choose between two crystal orientations, the Z-cut and the X-cut. A Z-cut crystal provides a higher electro-optic coefficient, which results in more efficient modulation. However, that same Z-cut crystal generates unwanted acoustic waves through the piezoelectric effect, adding system noise that the X-cut crystal avoids. Pure EO crystals are the best option for speed, provided the system can accommodate high-voltage drivers and manage the resulting acoustic noise. In the data center, the goal is scaling routing networks to massive port counts, like 128 by 128. The branch for massive scalability leads to the hybrid MZI SOA approach. Pure Mach-Sender interferometers, or MZIs, hit a limit at scale. Fabrication variability typically holds single elements to a crosstalk ratio of -20 decibels. Pure semiconductor optical amplifiers, or SOAs, also face issues when scaled. Chaining them together creates compounding noise from amplified spontaneous emission. The hybrid solution integrates both MZI and SOA components onto a single monolithic chip. These components divide the labor. The MZI provides low-loss routing, while the short SOA sections act as gates that absorb leakage signals to enhance the extinction ratio. This Cambridge University study proves this architecture's performance. For a 2x2 switch module, a single pass incurs a power penalty of just 0.1 decibels. When simulating a massive 128 by 128 port router, the penalty remains manageable at 2.4 decibels. Achieving this level of port scalability requires moving beyond legacy components and accepting the fabrication complexity of hybrid MZI SOA circuits. Buying an optical modulator based on top-line specs without matching the physical mechanism to the system's true bottleneck leads to poor signal quality and equipment damage. This evaluation scorecard maps the 3 technologies to specific engineering requirements. Industrial laser engineers should prioritize acousto-optics. Focus your budget on wavelength-matched crystals and precise aperture sizing. Telecom architects require Lithium Niobate Electro-Optic Modulators. You must account for the footprint of high-voltage drivers and choose the crystal cut that best manages your system's acoustic noise. Data center scalers must use hybrid MZI SOA arrays for large port counts. This single monolithic approach is the only physical way to scale past 16 by 16 without significant signal-to-noise degradation. Successful optical engineering relies on matching a device's physical limitations to the specific problem at hand.